Hi folks, this is the video for 1.4 relating polynomial functions and equations. The main goal of this lesson is going to be to graph polynomial functions by examining their properties and general shapes without the use of a graphing calculator. So here are the different types of polynomial functions we've looked at so far: linear, quadratic, cubic, quartic, and quintic. The first terminology we need to know is the degree. The degree of a polynomial is always considered the highest power of the variable in the equation. So for example, if you have the polynomial negative 2x cubed plus 3x5 minus 3 plus x squared, for this particular polynomial, the term with the highest power is this, and the highest power itself is that. So we say the degree of that polynomial is 5, or that's a quintic polynomial. Again, because the highest power of x is 5. Definitions of what a polynomial function is. A polynomial function of degree n can be written in standard form such as an xn, an minus 1, xn minus 1, and so on and so forth. And what that's basically saying is you're writing a polynomial in descending order with the highest power of x at the front and the lowest power of x at the end. The coefficient of the highest power of x, we call that the leading coefficient. Okay, that's what we're going to be working with a lot in this lesson. So the goal here now is to try and explore the properties of some of the different polynomial functions. Some basic ones like the linear and quadratic, you already know what they look like. But some of the other ones, we're going to try and figure out what some of their properties are. So at this point in time, what I want you to do is, I want you to go ahead and graph these functions that I've given you. You can either do it algebraically, or you can use your graphing calculator to complete those graphs and then copy your solutions down over here. I'll give you a moment to do that, so you can pause the video, go ahead. Alright, so once you've gone ahead and graphed them, your graphs will look something like this. I'm just going to draw approximations of what your graphs should look like. You're going to have this graph look something like this. You're going to have this graph. Let's use a different colored pen here. Look something like this. You're going to end up having this graph look something like this. And this graph's going to look something like this. Again, these are just approximations. We'll move on to the next page. These graphs are going to look something like this. Something like that. This one's also going to look something similar to a quadratic, but not quite. This one's going to look like this. And the last two, they're going to look like this. Alright, so once you've done that, that's the general idea. Let's go back and label what kind of graph these are, or what type of degree they are. Linear is degree 1, so we call that an odd degree function. Quadratic is degree 2, so that's an even degree function. Cubic is degree 3, so that's again an odd degree function. A quartic is even, and a quintic is also odd. So what we're going to do now is we're going to compare them odd degree versus even degree, and positive leading coefficient versus negative leading coefficient, and we're going to try and generalize some of the properties that we see, or some commonalities that we see. So let's take a look at even degree polynomials first. So we got the quadratic, the quartic, those two that we want to consider. You'll notice that whenever you have an even degree function and the positive leading coefficient is there, so the number in front is positive, like here and here, then what we end up happening is we end up having graphs that open upwards, right? Both the endpoints are going upwards and they're opening upwards. So we're going to write that down. When an even degree function has a positive leading coefficient, it's going to open upwards. Similarly, the negative leading coefficient, right? So there and there, those ones are going to be opening downwards. Okay, let's see what we observe about the odd degree polynomials. So the quintic with the leading coefficient, it's got that shape. Cubic with the leading coefficient, it's got that shape. And even a linear, it's got that shape. So you'll notice in all three of those, the pattern is they are rising from left to right. So what we say is they fall on the left and they rise on the right. Right? Or we can say rising from left to right. Similarly, with the negative leading coefficient, you'll see it's the other way around. They are rising on the left, falling on the right. Rising on the left, falling on the right. Rising on the left, falling on the right. So we'll go ahead and write that down. Rise on the left, fall on the right. So those are some common properties that we have observed out of all the different functions we have evaluated so far. And we're going to try and use these properties to try and generalize evaluating these functions or examining these functions. So here's our next set of definitions that we need to know. For the graph of any polynomial function, a point where the graph changes from increasing to decreasing, those are called our local maximum points. And a point where the graph changes from decreasing back to increasing is called a local minimum point. So what this means is, if you take a look at the example below, here we have a graph that is upside down w, so that's going to be a negative quartic function. We'll notice that up here the function was increasing, now it's decreasing. So this point it changes from increasing to decreasing. So that's going to be a local maximum. Similarly, down here it was increasing, and then at that point it changes down to decreasing. That's a local maximum. Here you have a function that was decreasing, changes up to increasing, so we have a local minimum. Okay. We're going to need to use all these things together to try and sketch some of these graphs here, which is what our next example is. So now the goal is to try and use some of the properties that we've learned to come up with the graphs of these polynomial functions. So the first way we're going to do this is we're going to go ahead and just get a general idea of what our graph's going to look like. By looking at this function, f of x equals negative 2x cubed plus 4x plus 4, I know that this is a cubic function and it's got a negative leading coefficient. Negative leading coefficient, I'll abbreviate that with LC. So I know a general shape of this graph. If I refer back to my chart here, I know that a cubic with a negative leading coefficient, it's gonna look something like that. That's the kind of graph I should be getting. Of course, the maximum and the minimum points might be changed a little bit depending on the function, but that's the general shape of the graph I should be getting. So the first thing that I'm gonna do is I'm gonna go ahead and graph this using a table of values. I'm gonna plug in some points and I'm gonna come up with those and I'm gonna graph it. So let's do that. So I'll use the following points: negative 2, negative 1, 0, 1, and 2. So let's go ahead and plug those in. I'll give you a moment to plug these in and also try the next example at the same time. Table of values, use the general points, and then create the general shape of that graph. Alright, so once you've done that, the points you will end up with are going to look something like this: negative 2, 12, negative 1, 2, 0, 4, 1, 6. 2, negative 4. And my first step is going to be to go ahead and plot these points. So I'm going to have to adjust my scale accordingly. So when I'm setting this up, I'm going to say this is 0. Points are going up factors of 2, so maybe I can go up in 2s. Will I have enough for that? Yeah, I should have enough for that. So I'll go 2, 4, 6, 8, 10, 12. And again, negative 2, negative 4, and so on and so forth. And when I go ahead and do it this way, it'll be 1, 2, negative 1, negative 2. I'm going to go ahead and plug those points: negative 2, 12, negative 1, 2, 0, 4, 1, 6, and 2, negative 4. Now the points is easy. The connecting part is where you have to use this idea here. It's a cubic function, negative leading coefficient. I know that generally should be doing something like this. So when I connect the dots, I got to keep that in mind. So when I'm connecting them, this is what I'm going to end up with. When you try to connect them, try and do it in one smooth motion. You don't lift your pen up along the way. It's supposed to be a nice smooth curve, not a graph with rigid edges. It's a little bit tricky to do on the tablet here, so mine might not look as nice and pretty as yours, but you get the point. So that's what the graph's going to look like with the negative leading coefficient. Similarly, for the next one, you can go ahead and complete that, and the points you will have gotten is this: -2, 12, -1, -1, 0, 0, 1, -3, 2, -4. These points, -2, -1, 0, 1, 2 are generally the standard that we use. Sometimes we have to use more points to try and give us a better idea of what the function is doing. In this case, I will need one more point on the positive side just to kind of complete the shape of the graph, 327. And you'll see in a moment why I need that. I'll set up my scale primarily based on these numbers here though, because that's what my graph's going to be focused on. So let's see, again I'm going up by 2, so I can do that. 2, 4, 6, 8, 10. I'll just set that as 10, so I know I'm going up by 2s. And 1, 2, 3, 4, 1, 2, 3, 4, -4. So now I know my scale is up by 2s and up by 1s along the x-axis. Let's graph the points. -2, 12 up here. -1, -1, 0, 0, 1, -3, 2, -4. And what you'll notice is that I know it's a positive leading coefficient and it's a quartic function. The general shape of that should look something like this. I should be opening upwards. So I know that when I'm graphing this, I need to know that my function is going to look something like this. Actually, let me leave it more specific, something like a W opening upwards. That's the general shape. If I try and connect these points, I know that I'm not going to get a W that open upwards. In fact, I'm going to get W sort of that looks like this. And I know as a result, this does not match up with the shape I should be getting, so I know I need to pick another point. And when I pick another point, +3, I get a value of 27. So that point's going to end up being somewhere all the way out here, and this will help me complete that graph. So now when I go ahead and join it, I will get that W shape that I was looking for with the positive leading coefficient. So this is where we have to use the idea of the general patterns and general shapes of these polynomial functions, because if we just use the table of values, we might not get the correct graph unless we know we need to get more points to complete the graph. Using table of values to create graphs is something you've been doing for a very long time. In our next example, we're going to try and figure out a different way of graphing these polynomial functions. And in fact, we're going to try and use their intercepts to sketch the graph of this polynomial function. So first thing you'll recognize is that it's a quartic function. If I want to find the intercepts of this quartic function, I need to first go ahead and factor this. This is where we're going to apply everything you've learned so far in this chapter. So we now know how to use the factor theorem and the remainder theorem and the factor property to try and factor a polynomial of degree 4. So let's go ahead and do that first. I'll give you a moment to go ahead and factor this polynomial. Once you've got the factors all figured out, then I'll go ahead and show you how to create the graph using those intercepts. Alright, so once you've had a chance to go ahead and factor that, this is what your factoring is going to look like. I'll walk you through the process. I started off by identifying all possible factors of 6, which were 1, -1, 2, -2, 3, -3, 6, -6. I tried one of them. I tried x equals 1. Lucky for me, it worked. So I knew that x minus 1 is a factor. Once I've got that part figured out, I can then use synthetic division to go ahead and use x equals 1 and figure out the remainder of the polynomial. And in doing so, I ended up with this polynomial right here, which was a cubic. And then again, I repeated the process again. I started off with the last amount 6, listed all the factors, tried one by one. So 1 didn't work this time, -1 didn't work this time, 2 did work, so I knew that x minus 2 is a factor. Okay, I did the synthetic division on just that part, the cubic polynomial, and I got the quotient of a quadratic this time. So as a result, my polynomial, original one that I started off, can be factored into x minus 1, x minus 2, and that quadratic right here, which I can further factor into those two binomials. So the fully factored form of this polynomial is x minus 1, x minus 2, x plus 3, and 2x minus 1. Once we've got that, the information that those factors are giving us are the intercept. That was the goal of this problem in the beginning, to figure out what the different x-intercepts are. So based on that, I know that my x-intercepts are, and they are the zeros, so 1, 2, -3, and positive a half. X-intercepts, or I also call them the zeros. Once you've got the zeros figured out, what we're going to do now is go ahead and graph those zeros on our axes and try and fill in the gaps using some strategic key values. So let's go ahead and plug that in. I'm going to quickly create a graph on the side here with the zeros that I've come up with. So let me draw a quick grid here. Let's draw one down here. And you can go ahead and create a grid as well. And I already know that my graph is going to be heavy at the bottom part and not so much at the top, so I'm strategically going to do that. And if you don't know that, that's fine, you can create it. Then if you realize later on that your graph is sort of too squished in, you can adjust your grid accordingly, you can adjust your axes accordingly. Okay, so I'm going to set it up that way. You can also do the same thing. Once I've got that figured out, I'm going to go ahead and label my grid so I know what units and what amounts I'm going to be going up by. The left and right, I'll go up by ones. So 0, 1, 2, 3, 4, 5, and 1, 2, 3, 4, -5. Going up and down, I'm actually going to have to end up going by a scale factor of 6. And actually, I'll leave that out right now because I'm going to see in a few minutes that I need to do that. I'm going to go ahead and now graph my intercepts. The intercepts I have are at x equals 1, x equals 2, x equals -3, and x equals positive a half. Perhaps maybe I should have used a different grid over here for my x and y axis. I could have gotten a nicer, neater graph, and I can make that adjustment if I want to as well. In fact, let me go ahead and do that. It might come in handy. Instead of going up by ones, I'm going to go up by half. So I'll make this 1, 2, 3, 4. We'll make this -1, -2, -3, and so just make my graph a little bit nicer to work with. That's all. Now when I go ahead and create the dots, let me use a different color here. I will get my zeros at x equals 1, x equals 2, x equals -3, and x equals positive a half right here. Those are my zeros that I'm going to be working with. 4 zeros. I know it's a quartic function, so I know it's going to be a W-shaped function, either opening upwards or it's going to be opening downwards. Now, one of the things that I can observe is if I go back and take a look at the leading coefficient over here, I know that the leading coefficient is positive. So I know that my graph is going to be opening upwards. So I know that the general shape I should expect of this graph is sort of an W opening upwards. And now I've got my 4 intercepts that I can work with. I just need to fill in the gap. So I know that I'm going to have a graph going upwards from here. I should have a graph going upwards from here. I just need to fill in the gaps. So to fill in those gaps, I'm going to pick some key points to help me figure out where the hills and the valleys are. So let's make another table of values here. Now this method here using intercepts will only help us come up with a nicer, more accurate looking graph. It'll help us pick the points strategically on a table of values. So one of the points I'll pick is, say, perhaps -4 to test and see what's happening to the left of my x-intercept of -3. I'll pick the one in between the 0 and -3, so I'll pick, say, -2. I'll pick another one to see how far down I have to go, or how far up I have to go, -1. I'll pick one between half and 1, so 0.75. I'll pick one between 1 and 2, so say 1.5. And I'll pick one outside of 2 to try and get the endpoint over there, so say perhaps 3. So I'll let you go ahead and figure those out. You can pause the video here right now and find those values. Once you figure those out, we will compare the answers. Alright, once you figure those out, the values I ended up coming up with were -4, 270, -2, -60, -1, -36, 0.75 and 0.59, 1.5 and -2.25, and lastly 3 and 60. So you'll notice the points are very big and very small at the same time. So when you're setting your y-axis, it might be better if we set some numbers that were multiples of another big number. So what I'm going to do is I'm going to set my y-axis, say multiples of 6, just so I get a nicer graph here. So I used red here, let me use red again. So -6, -12, -24, -36, -48, and -60. Okay, so this is what I'll get. Now let me try and go ahead and plug these points now. So the points I came with -4 and 270, it's going to be way off the chart, so I know it'll be a point up there. -2 and -60, it's going to be a point down here. -1 and -36 will be a point over here. 0.75 and 0.59. So 0.75 will be here, and 0.59 is very, very close to that value. So just actually be a little blurb up here. And it's almost a blurb you can't even see. 1.5 and -2.25. Again, it'll be about a blurb down here. And lastly, 3 and 60. So going up, the way I've scaled, it's going to be off the chart, it'll be up there somewhere, so it's going to be a big positive value. One of the other points I can use, which I didn't put on the table of values, is I can also use the y-intercept over here. I know that's going to be the y-intercept, so I can also use that as the y-intercept. So let me go ahead and plot that here. The y-intercept is -6. So now it's a matter of creating a smooth graph, and you'll have a general shape. So the graph's going to look something like this, and this might not turn out really well, but we'll try it. Going up. It's going to do a little blurb there, come down. It's going to do another blurb down here, and then connect back up. And that's going to be the graph that I end up with as a result. Okay, that looks like a W. It's got a big valley and a tiny hill at the top, another small hill, another small valley at the top over there as well. I know the general shape looks okay, the end behavior makes sense, and I've got a W looking shape, so that's the graph that I do end up with. Now on to the next example that I've got over here. The next example is for you to try. So take a look at this example, give that a try. Again, the process is the same, fully factor it, use the intercepts, fill in the gaps using table of values, and create a general graph. I'll give you a moment to go ahead and try that. Let's pause the video here, and we'll compare answers in just a moment here. Alright, so once you've had a chance to factor that, these are the factors that I ended up with. It was a cubic with a GCF of x, so right away I ended up with a quadratic. Once I had that quadratic, I could easily factor it into this form right here. And from there I figured out that my x-intercepts are simply 0, -3, and a +2. I can also figure out that my y-intercept is going to be 0 because there's no constant over here. It's the same as having a 0. So I had these 4 points to work with. All I have to do now is plug those points on a graph and then fill in the gaps using a table of values. So let's take a look at our graph here. So on my graph, I've got to set up a grid. What I'll do is I'll first go ahead and plot the points for the left and right. So x-axis, I think I can go up by 2's here. So 1, 2, 3, -1, -2, -3, -4. This gives me a nicer, wider graph. The y values I will check in a bit and I'll set my scale accordingly. So I know that I have x-intercepts at 0, -3, and +2. I also know that it is a cubic function with a positive leading coefficient. So cubic positive leading coefficient. So I know that based on that, the shape I should be expecting is something like this. That's the general shape I should be expecting, okay, with different levels of hills and valleys. So let's try and keep that in mind as we do this, which means I know that I should have something that's going to be going downwards towards here and something that's going to be heading up from here in this direction. I need to plug in my 4th point, which was y-intercept of 0, so I've already got that here. Now, time to make some table of values. I will need to test some points. Need to test -4. So my table of values, let's test -4. So I get end behavior. Test a point between -3 and 0, and in fact I'll test a couple of them. I'll test -2 and -1. 0 is already there. Need to test a couple of points here on this side, so I'll pick one between 0 and 2, +1, and then I'll pick one outside of 2 to get the end behavior again, +3. In case you're confused how I'm coming up with those points to pick, I'm just finding points in each region. I want one in this region, a couple in this region, one in this region, one in that region, to kind of get an idea of what my graph is doing in each of those regions, how deep the valleys are and how high the hills are. Alright, go ahead and complete that graph, and then we will compare. Alright, so once you've had a chance to complete your table of values, you will find out that the numbers we got were -4, -24, -2, 8, -1, 6, 1, -4, 3, 18. When I'm setting up my y-axis, I'll realize that there's a lot of multiples of 8 and 4 here. So I set up my scale factor going up and down by 4. So 4 and 4, that's the scale factor I got. Then I went ahead and plugged in those values, got each of those points, -4, -24, -2, 8, -1, 6, 1, -4, and 3, +18. Now it's just a matter of connecting those dots, given the key idea that we do know where our function is going to look like. So what we should end up getting is a graph that looks like this. It's going to have a hill here. It's going to pass through that intercept. It's going to pass through that intercept. And again, it's going to keep on going up in that amount. Again, it matches up the general shape that we were expecting, falling on the left, rising on the right. It's a cubic function, passes through those intercepts. Your graph should probably be a bit more smooth. With the tablet here, it's a little bit hard to kind of get that smooth curve. Try and draw that graph without lifting your pencil, unlike what I was doing, and you should get a nice smooth curve. Off to the next part here. We just discussed that the x-intercepts are considered the zeros of the polynomial because they are the values of x when the function is 0. The zeros of the function are also the roots of the related polynomial equation. A polynomial equation may also have repeated roots. So for example, if you factor this polynomial out here, x squared minus 2x plus 1, then the factors you're going to get are x minus 1 and x minus 1, which can be written as x minus 1 squared. We say this expression has a root of x equals 1. However, because x minus 1 is repeated root, we say this root has a multiplicity of 2. The reason why it's 2 because it repeats itself 2 times. Similarly, if I was going to go ahead and factor this cubic function here, x cubed minus 3x plus 3x minus 1, you would get the factors x minus 1, x minus 1, x minus 1. you'd get them 3 times. And since it's repeated 3 times, we say that that root of 1 has a multiplicity of 3. So in general, whenever a polynomial equation is written in fully factored form, the exponents of each factor represent its multiplicity, or the multiplicity of that factor specifically. So if you have the general form x minus a to the power of m, x minus b to the power of n, x minus c, then we say that root a has a multiplicity of m. It's going to repeat itself m times. Root b has multiplicity of n. It's going to repeat itself n times. And lastly, root c will have a multiplicity of, when there's nothing here, there's always a 1, they'll have a multiplicity of 1. So the next question is, how does multiplicity help us graph a function? So here is a common pattern here. This graph has a 0 of multiplicity 2. So here is a 0 of that graph. Let's use a different color pen here. Here's a 0. But it's got a 0 of multiplicity 2. Here you've got a 0 of multiplicity 3 right here. One of the things you'll notice is that when you've got a multiplicity of 2, this graph, it barely touches its 0. It just passes and bounces right back off. When you've got a multiplicity of 3, this graph is going to actually pass through its 0 in the continued direction. And that's what multiplicity does for us. The graph of x minus 1 squared, which is that one over here, touches the x-axis at x equals 1, but it does not cross it. However, the graph of x minus 1 cubed, it crosses the x-axis at its 0. So in general, we say that whenever a function or a polynomial has an even multiplicity, then the graph touches the x-axis at that intercept, but it does not cross it. Whenever a 0 has an odd multiplicity, the graph crosses the x-axis at the related x-intercept. So once again, a quick review. Whenever a graph has a root that has multiplicity of an even number, it's just going to touch that root. Whenever a graph has a root of multiplicity odd number, the graph is going to pass through that root. Also note that different roots of a function can have different multiplicity and thus have different behavior at those roots. You can also have a combination graph. So for example, I could also have had a graph that would have done something like this. It could have done this and then bounced right off over there. Right, so at this root, it would have passed through you. You would have known that that's got an odd multiplicity. And this one, it just touches and bounces off, so that one would have had even multiplicity. So you can have both of those happening within the same graph, or you can have only one of them happening within the same graph. Our next goal is going to be to use this idea of multiplicity, and of course zeros, to try and create the graph of polynomial functions. Sometimes we get nicer graphs if we use this concept of multiplicity. So let's go ahead and try and graph these functions using the idea of multiplicity. I've already given you the fully factored form because I don't want you to spend your time on that for this part of the problem. So the first thing we're going to recognize is, based on this factored form, we have two roots or two x-intercepts. So the first root is x equals 1 and the second root is x equals negative 3. And what I'm going to identify is that the root that's x equals 1, this root has a power of 2, which means I'm going to say this root's going to have an even multiplicity. Similarly, this root of negative 3, it has a power of 1, so that means it's going to have an odd multiplicity. And the concept that I just learned a couple of minutes ago is, whenever we have an even multiplicity, the graph is going to just touch. And whenever we have odd multiplicity, it's going to pass through. So So that's the idea we're going to use to try and create our graph. Okay, so first things first, I'm going to go ahead and graph these 2 points and then come up with a general table of values to fill in the gaps. The idea of filling in the gaps is still the same. I'll let you go ahead and put those points on a graph, pick a table of values of your choice, and complete the graph. We will compare our answers in just a moment, so pause your video and try that problem. So once I've had a chance to go ahead and create an axis, plot the 2 roots at -3 and +1, I now have a chance to pick some other values to fill in the graph. So some of the values I'm going to test something to the left of -3, so I'll pick -4. Another value I can test is between -3 and 1, so I'll pick 2 of them, -2 and -1. And I also know that my y-intercept I can figure out when x is 0, so I'll even try that, x equals 0, get the y-intercept. And I'll pick 1 point to the right of x equals 1 to get the end behavior on that side, so I'll pick, say, +2. I'll pick those points, I'll plug them in, and I'll get some other values to test. I'll let you go ahead and do that, pause the video, fill those in, and then compare your answer. Once you've had a chance to do that, what you'll get is the following: -4, -25, -29, -1, 0, 3, 2, and 5. So now when you go ahead and plot that graph, you will get the following. So -4, 25 is going to be a value off the chart somewhere down here. I'll keep that in mind. -2 and 9 is going to be somewhere up here. -1 and 8 is going to be up here. 0 and 3 is going to work out to be over here. 2 and 5 is going to work out to be here. Because I know this is going to be a cubic function when I expand it, it's a positive leading coefficient, I should get a shape that kind of looks like this. And I can confirm that when I connect the dots. I know I had a point all the way down here, so I'm going to start over here. This root, -3, has a multiplicity that's odd, so I'm going to be passing through that root, going all the way up to this point, coming back down, passing through here. This root of x equals 1 has an even multiplicity, so I'm just going to touch that root and then bounce right back up, passing through that point and all the way up. Of course, I kind of missed that point, so let me redraw that. So passing through that point all the way up, and of course I get the shape that I was expecting, a cubic function with the 2 roots with those multiplicities. So that's the final graph that we should be getting. Of course, you can pick more points in between and get a much nicer graph, but that's the bare minimum that we do need. I'll let you finish off one more example over here. You try it. Pause the video again, give that a try, and I will show you the answer once you've had a chance to try it yourself. Once you've had a chance to try it, this is what you'll end up with. You'll get that the 2 zeros are -2 and +1. The -2 has a multiplicity of 3, so it's going to be passing through. It's odd multiplicity. The +1 has an even multiplicity. It's going to be just touching. We know this is going to be a quintic function, power 5. So we should generally have an idea what kind of shape it's going to be. One of the other things I got to watch out for is, because there's a negative here, we have a negative leading coefficient. So that should also be giving you an idea of what kind of shape we're going to be looking at. Because of the fact that it's a power 5 with the negative leading coefficient, I should generally be expecting something that's falling on the left, sorry, rising on the left, falling on the right. So something that should be doing something like this, with of course a varied amount of hills and valleys. Could have a couple more hills and a couple more valleys in there, but that's the general shape I should be expecting. With that in mind, I can now go ahead and pick some other values to complete my graph. So what I've done is I have picked the scale, I picked some values that I need to test, graphed my intercepts, adjust my scale accordingly, and all that's left for me to do is graph those points and connect the dots. I have a point at -316. I picked my scale, a scale factor of 4, so -316 will be a point up here, -1, -4 will be a point down here, 0, -8 will be a point down here, and 2, negative 64, will be a point all the way off the chart. So I'm just going to pick a point all the way out here, just so that I know that that's where I'm going to be ending up. Connect the dots. I know I'm going to be rising on the left, falling on the right. This is where you really need to know what the graph looks like. Otherwise, you have no idea how to connect those dots. I know my graph's going to do something like this. It's going to bounce back from here. It's going to go. It has to pass through that 0 because that was the one that was odd multiplicity. This 0 is going to barely touch and bounce back, and then I know it's eventually going to end up at the bottom over there. So my graph should have a shape that kind of looks like this. Mine is not very nice and smooth because again of the tablet, but yours should be a bit smoother than that. So that brings us to the end of this lesson. Hopefully you've made the connections and you realize that we need to have all sorts of different information to try and come up with a nice smooth curve of polynomial functions. Good luck with your homework.